It is my pleasure to welcome you to November's Wednesday webinar, everybody. We are joined by the amazing Dr. Alan Garfinkel, who I had the pleasure of meeting in person this summer. I followed him for decades, but in a great way, Alan. I'm a good stalker. Followed his work.
You certainly are.
And when I attended this mathematical modeling for life sciences workshop at Harvard University this summer, it was a wonderful opportunity I actually had the opportunity to teach kids partial differential equations. And these were high school kids, like of all different backgrounds. Some of them had algebra, some had algebra 2, some were in AP calculus, and we were learning about these change equations. And it was just amazing to see them be able to wrap their minds around a concept that is usually behind 3 calculus semester long courses. It's just an awesome plug for accessibility, right, for students and for rigorous mathematical concepts being accessible. And I also wanted to show that this relates to Alan's talk today. I tweeted about it, or I don't know what you call it now. I X'd about it. I tweeted about it this weekend. Tweeted's better. I picked up this calculus book at the thrift store. It cost $1.99, which is a 50-cent increase from when it was published in 1944. And if you read the table of contents, it reads like a modern calculus book. It reads just like the AP calculus topics that they teach in sequence. And it was fascinating to me to think from 1944 to 2023, what has changed as we're teaching these concepts to students? And with that introduction, I'm going to turn the time over to Dr. Alan Garfinkel to stretch our minds a little bit in this arena.
Thank you so much, Lindsay, and thanks to all of you for the invitation. I want to talk about what we've been doing in both modeling and dynamics and in statistics. So I got a lot of slides, so let's see how many I can get through. So let's first talk about dynamics. And how do we teach modeling to biology undergrads? And by undergrads, I mean undergrads. These are freshmen. These are 3 months out of high school. So please don't think, oh, well, this is advanced college students. Of course, they can understand boutique concepts in boutique courses for elite students. Absolutely not. These are freshmen at a large state university. So where did this get started? It got started around year 2010 with 3 major position papers, brochures from major national organizations. In 2009, the Howard Hughes Medical Institute and the American Association of Medical Colleges, which is the Association of Medical Schools in the United States, put out a brochure called Scientific Foundations for Future Physicians. And they asked for certain undergraduate competencies. And these undergraduate competencies include being able to quantify and interpret changes in dynamical systems using positive and negative feedback. They wanted you to understand how the student to understand how feedback mechanisms can lead to oscillations, for example, in glucose. They wanted you to understand how to use the principles of feedback control to explain homeostasis and disease. So that was 2009, and it addresses physiology and medicine. In 2011, the National Science Foundation and the AAAS put out a joint brochure, and they said the same things, but this time about biology, not medicine. Studying biology requires modeling, computation, and data analysis, by the way, modeling, dynamics modeling. That's what the National Science Foundation wants. So now you ask, okay, I hear you. What kind of math do we need to study these feedback loops? And the answer is very clear, and it comes from no less than the National Academy of Sciences, who in that same period said, this is what we need. Mathematical computational methods should be taught on a need-to-know basis. Is that what we are doing in AP Calculus? And by the way, when I say calculus with that sneer in my voice, I mean the course that is standardly called AP Calculus. I do not mean the concepts of derivative and integral, which are very important. Is this what AP Calculus classes do? And the answer is no. They do not. They teach you, memorize these tricks, because 2 years from now, you're going to thank me when the teacher invokes them. And I think that's bad teaching. I really do. The emphasis, they continue. The emphasis should not be on the methods per se. What is what is calculus? Calculus is the emphasis on the methods per se. And the applications are sort of, well, okay, if 17 whales are added to the population, there's sort of trivial little examples. The emphasis in calculus is on the methods per se. So you say, okay, modeling, that's differential equations. So they have to take a class in Diff-EQ. And before they take a class in Diff-EQ, they have to take Calculus 1 and Calculus 2. And before they take Calculus 1, they have to take pre-calculus. And before they take pre-calculus, they have to take pre-pre-calculus. No. The National Academy of Sciences says ordinary differential equations made tractable and understandable via Euler's method, which I'm going to talk about, without any formal course in differential equations. So this is, don't talk to me, talk to the National Academy of Sciences. This is what they're calling for. So I want to tell you about our class. We call it Life Sciences 30. These are freshman students. There is no prerequisite. We offer it as an alternative to the math department's Calculus for Life Sciences, and we get about 2,000 students per year, as opposed to 70 students who choose the Calculus for Life Sciences option. So this is the slide 1 on the first day of class. You put a bunch of sharks and a bunch of tuna in a big old patch of ocean, and what happens? And the students say, well, the sharks eat the tuna. And you say, yes, exactly. Then what happens? Now you have a lot of sharks and very few tuna. Is that a stable situation? Ooh, no, it isn't. So there's going to be further changes. So what are the further changes going to do? The sharks are going to die. The tuna are then going to grow. Why do you need mathematical modeling? Because we can't sit here on our duff and intuit how the system is going to behave. We have to make a model. So, next question, how do you make a model? Well, you start by choosing some state variables. Here, the number of sharks and the number of tuna are our state variables. And then you just ask, what makes S go up? What makes S go down? Why does it have this form? What's the birth rate there? Why is it multiplied by the number of sharks? Same thing for tuna. What makes tuna go up? What makes tuna go down? And then the all-important shark meets tuna term. And with a shark meets tuna term is a quadratic. It's a nonlinear term. Beta is the probability that a shark-tuna encounter results in the death of the tuna and the feeding of the shark. And this is how we assemble a model of this feedback process. So this is ecology. Let's cut to a completely different subject. Let's talk about epidemiology, which has been in the news a little bit. What's the story in epidemiology? Well, we have two kinds of people, tuna and sharks. We have infected people who are the sharks, and we have susceptible people who are the tuna. And the susceptibles feed the infecteds, but the infecteds reduce the number of susceptibles. So what do? We put that into a model with the magic term beta SI, means susceptible meets infected. And with probability beta, the number of susceptibles goes down one and the number of infecteds goes up one. Beta is the parameter you would modify to test social distancing, test a mask policy, test a vaccination protocol. So in the third week of class, we can ask the student, simulate this model and tell me how much of a vaccination program you would need in order to bring that infection down, in order to bring that epidemic down. We stress dynamical analogies. The shark tuna model is exactly like the model for a chemical reaction in which sodium bumps into chloride and they form sodium chloride. So there's a complete dynamical analogy between population dynamics and chemical population dynamics. So now we have a model. We have all of these terms down, and then we collect these terms into a change equation. And the change equation just says the change in S, and we add up all the positive terms and we subtract all the negative terms. And this is our model expressed as a change equation. Okay, that's nice. What do you do with a change equation? Here is the change equation for the shark tuna. What do you do with it? Here's what we don't do with it at all. No symbolic manipulations. No, the derivative of sine is cosine, substitution of variables, integration by parts. We don't touch those equations with symbolic calculus techniques. And the reason is that shark tuna equations have no analytic solution. And so that is simply calculus fail. So the student comes to you and says, oh, I love this shark tuna dynamics. I really want to understand this. And good news, I took a year of calculus and I got an A++ in calculus. How does that help me understand the shark tuna model? And the answer is it doesn't. Throw out everything you know, especially the idea that you can bang on equations with symbolic techniques and produce solutions. Forget that, because it's what got you here today, but it is not going to get you there tomorrow. Because all the procedural tricks that constitute AP calculus go out the window on the first day of real life. And I mean all of these: L'Hopital's rule, finding the antiderivative, substitution of variables, rules for differentiating famous functions. All of these bullet points of AP calculus go out the window. And some of my students have obviously had AP calculus, and I can always tell when they've had one of these calculus from hell classes, because I just ask them, what is a derivative? And if I get this answer, I took calculus. The derivative of x squared is 2x. You put the exponent in front of the variable, and then you have to drop the exponent by 1. This is poor understanding of math, and this is very poor teaching tied to a very poor concept of math. Mike Reed from Duke is a mathematical biologist who is still very active in publishing. 35 years ago, he says, first problem was to differentiate x to the sine x. And I said, that's what's wrong with calculus. Why should I spend all my time worrying about how to differentiate stupid looking functions like that? It means that the teaching of calculus has developed into a series of technical hurdles bearing very little relation to what they're supposed to get out of the course. And that's true today. So enough bashing on calculus. Let me tell you what we're doing. We are using 20th century math concepts, not 19th century math concepts. The first one is the concept of state space. This is a geometric space in which the system state, T0, S0, number of tuna, number of sharks, is a point in tuna shark space. In a patient, the levels of glucose and insulin are a point in glucose insulin space. And then over time, that state point moves around in state space. And that's what change is. So what is the change equation? The change equation is a machine like Siri or Google Maps for spitting out the appropriate change instruction for your current state T0, S0. And it says, if you are at T0, S0, head in the direction of the change vector at a speed equal to the length of the change vector. So we have a new idea. Don't think of this as the change equation as a differential equation, because it's not an equation. We're not going to be substituting the square root of x on both sides. We're not going to be using equations. The change equation is a function from state space into tangent space, and it assigns the correct change vector to your current point. Then we take that change vector, multiply it by time units, and now we can write the change vector right onto state space. And you're beginning to see the instructions and how they're going to play out. So here is the 20th century. This is what we teach in the first 3 weeks of our class. Now, I drew 3 change arrows here, but we need a lot more. So we're going to use a computer, which I understand computers were invented some years ago, although calculus pays very little attention to that fact. So we use a computer to draw all these change arrows, and the students are going, oh, wait a minute, look at this. I see what's going to happen. I see what's going to happen. This populations are going to oscillate. And you say, yes, very good. Now, I traced it out with my finger, but I'm going to use a technical and more accurate method called Euler's method, which means that we take a little straight line step here at every little time step. And so we approximate the curve with finite little steps. And this is about 1,000 little steps, again, done with a computer. And so you say, oh, that's a nice curve. What is the equation for that curve? And the answer is there is no equation for that curve. Period. But as I was saying, it's a very different concept of what is math. So if I say to you, I'm integrating a differential equation, what picture comes to your mind? If it's that, then I think you have the wrong concept of what dynamics is. So I'm doing this, and you say, oh, Alan, what are you doing right now? And I say, oh, I'm integrating a differential equation. That's what integrating a differential equation is. Now, you don't want to do this by hand, so we teach a little bit of Python. This is less than 10 lines of code, and it generates this whole figure with the change arrows and the curve. So that's what I'm saying. We have the 19th century view, and we have the 20th century view. And the 20th century view is better pedagogy than the 19th century view. but also from the research point of view. And this is what the National Academy of Sciences was talking about. What does calculus do? It trivializes the problem in order to be able to apply the symbolic techniques. So you take a mass spring system and you assume that the spring force is given by Hooke's law, F equals kx, linear relationship. That gives you a linear differential equation. Ooh, that linear differential equation can be solved with calculus techniques. The derivative of cosine is minus sine. And you get to show off your calculus. And then the student comes to you and says, okay, I'm ready. I want to study some biological examples. And the first thing you have to tell them is throw out everything you know, because Hooke's law is false in biology. Here is cardiac muscle, all bone, cell membranes, all nonlinear spring functions. And so these can't be solved by calculus. So we do talk about the derivative. We stress the conceptual, that the derivative is the linear approximation to a function at a point. Here it is in 1D. Then in the second semester of the class, we talk about the 2D generalization, which is here. This is the linear approximation to the two-dimensional curved surface. We talk about integration. But what do we talk about integration? Not finding the antiderivative, which, as you know, is a very, very limited technique. We stress integration. What is it? You just stop one of my students on the campus and you say, what is integration? And they'll say, oh, add up the little rectangles. And you show how the total distance is equal to the distance traveled here, which is the velocity times delta t, and you add up the little rectangles. So this is what I'm saying from a research point of view, from what the student is going to get exposed to instantly in sophomore and junior years. And this is the problem. If you have a spherically symmetric charge distribution, a uniform distribution on a perfect sphere, we can use the integral and find the antiderivative of the constant function, and we can use calculus. Then the student takes a biology class and they look at an actual molecule and they want to get the field due to the charge distribution, and the only answer is add up the little rectangles. So that's our class and the outcomes. Lindsay, can you monitor the chat? And if there's relevant questions, absolutely speak up.
I will.
So we had a wonderful educational specialists group follow our class and do evaluations and follow-ups. This is what they found. Number one, our students had a much higher interest in math after this course than before. %80 of our students agreed with the statement, this course increased my confidence in my math ability. That's an interesting statistic. 94% of the students saw the real life application or relevance of what they learned. The math department had said, oh, but they must know calculus because if they're going to take physics and chemistry, they must know calculus. Well, here's the data. This is our course. This is the freshman calculus class. You see that our students earn A's in subsequent chemistry at a double the rate of the calculus students. Subsequent physics, our students earn A's at double the rate of the calculus students. And this is all in those papers. Underrepresented minorities earn A's or A pluses in Physics 6A at twice the rate of underrepresented minorities in Math 3 and calculus. So our DFW rates hover at around 4%. We'd love to get that better, but geez, I go to meetings where calculus instructors tell me that their DFW rates are 40% or 50%. And that is a scandal. So to wrap this half, we had a wonderful, Lindsay mentioned, we had a wonderful workshop at Harvard this summer, led by two superb teachers, Brendan Kelly and Jennifer Choker from Texas State. And we taught, we had 30 visiting faculty, and we taught them how to teach high school students, because these were the high school students that were enrolled in a class at Harvard Summer School to learn dynamics. So we taught the faculty, and the faculty taught the visiting high school students. This got written up. Lindsay's going to post the link. It's got written up in USA Today. And as a result of this, we have a lot of schools, from the very fancy elite schools to absolutely working class 75,000 student state universities. And they're all have adopted or are interested in adopting. So here's what I'm saying. Joel Cohn is an excellent mathematical biologist, and he's saying that biology is going to dominate math. Biology is very, very big, and we want our math. And Jennifer makes the point very correctly. We've been talking about this all along, what is your valuation here? What does it mean to know mathematics? This is the calculus desideratum. We trivialize the class of differential equations, linear differential equations only. Nonlinear problems do not come to us. Given a representative of a trivial class of differential equations, can you reproduce the specific appropriate trick to obtain its solution on command? Is that your concept of what good in math is? Is that what you're trying to teach your students? Or would you rather have them be able to say something about the development or behavior of the system under different conditions by making a model? Okay, deep breath. Because I now move on to subject number 2, which is going to sound a little like subject number 1. So I want to talk about the revolution that is taking place in statistics, where if I said to you, what is statistics? Is it formulas, or is it understanding how to deal with complex distributions? So, reminding you of the first part of my talk, we talked about the 19th century, formulas, paper and pencil solutions, heavy assumptions. And then we talked about the 20th century. And made the point that the 20th century concept is better pedagogy. So now let's cut to statistics. So what's the short history of statistics? Well, we have a real breaking point, and the breaking point is mid-20th century. And mid-20th century, why mid-20th century? The birth of modern computing. So in the 19th to mid-20th century, no computers, formulas, we get proof theorems, but it's tough to prove theorems. So we have to make crippling, trivializing assumptions that everything in sight is a normal distribution, and we're only going to talk about the means and standard deviations. So we learn about the t-test, where you calculate the t-statistic and you plug it into this formula and you see what the outcome of the formula is, or a chi-squared test. But all of these are derived for the means and standard deviations of normally distributed quantities. In the late 20th century, we see non-normal distributions where the median and the mean are very different. And we see bimodal distributions, which you should not even begin to apply these formulas to. It's absolutely wrong. It is malpractice to apply these tests to these distributions. They violate the assumptions. So what was the purpose of the formulas? The purpose of the formulas was to calculate something called statistical significance, or to calculate something called confidence intervals. So in this short talk, I'm only going to talk about statistical significance, but everything I'm saying is also true of confidence intervals. What is statistical significance? The thing that the formula gives you? It's an estimate of how unlikely your result is to have occurred at random. That's the thing called the p-value. So you calculate the t on your data and you plug it into the formula, and the formula tells you that if t is bigger than 1.98, then p is less than 0.05. What does that mean? P is less than 0.05 means the probability of your result happening by pure chance is less than 5%. How can we do that? Well, in the old way, we have to prove a theorem. In order to prove a theorem, we have to make heavy-duty assumptions. First, very heavy-duty assumption. Groups A and B have to be normally distributed. Second heavy assumption, you have to use the mean value to describe the groups. Third heavy assumption, you have to use subtraction to compare the two groups. If all of these things are true, I can prove it, or a student can prove a theorem that the quantity t will be distributed like a theoretical distribution called t of x, and then you compare your result to the tails of the t of x to judge statistical significance. What's wrong with this approach? It has produced an epidemic of irreproducible results and scandals. In this month, hormone replacement therapy causes cancer. Next month, hormone replacement therapy does not cause cancer. Aspirin prevents heart attacks. 6 months later, aspirin does not prevent heart attacks. How could so many studies be wrong? Because they relied on this concept of statistical significance. And this has now been identified at the highest levels as scientific irreproducibility. One of the big contributors is bad statistics. So as I said, what's wrong with the formulas is that the formulas are based on these heavy assumptions. Normal distributions as n approaches infinity, must use means and standard deviations. This is what we live with if we need to prove theorems. But these assumptions are absolutely crippling assumptions, even to our thought process. I saw this headline, average tax refunds up 40%. So I showed the headline to my class, and I said, based on this headline, which of the following is true? I can expect around $40 more. I can expect a bigger refund. Many people will get approximately $40 more. A typical refund will be $40 more. And E, none of the above. And of course, the correct answer is none of the above. I asked my class to do this. Here is the result. Here's the class poll. Only 22% gave the correct answer. 78% of the class gave totally wrong answers to this question. And when I showed this to them, they were all kind of crestfallen. And I said, why did you make this mistake? And the answer is because you bought something, you were conned into believing, and you bought the con that everything is normally distributed. Because if everything was normally distributed, these would all be true. But it isn't, and so it's not. So this assumption of the normal distribution in the face of data, which is not a normal distribution, is a major problem. The criticisms of the normal distribution that have now emerged scientifically are very, very decisive. They're very negative. People now talk about thick-tailed and long-tailed distributions, including tails at Amazon.com, songs at iTunes. The actual die-off here is much slower. It's a much longer and thicker tail than the normal distribution. So what's wrong with assuming a normal distribution model when you don't have a normal distribution? Well, one consequence is you get the stock market crash of 2008. How did that happen? Well, economists, mathematical economists, got the Nobel Prize in economics, which should be abolished. For the Black-Scholes equation, this is a differential equation that values the price of a derivative of an option. So one of the things that goes into the valuation of an option is how likely are big price fluctuations. If big price fluctuations are unlikely, then my option is more valuable. So built into the equation is this sigma, which they call volatility, but what it is the standard deviation of the price fluctuations. In other words, they're assuming that price fluctuations follow a normal distribution. Therefore, very little big deviations. But in a long tail, the number of large deviations is much, much higher, and you can't use formulas and t-tests. So if you estimate the likelihood of a catastrophic event is given by this, and the actual likelihood of a catastrophic event is given by this, you're going to make a very bad bet. And that's what everybody did. So just to keep on this theme, what do we suggest as an alternative to this mean value, the average, which is meaningful for normal distributions, but not otherwise? A very useful concept is the concept of the median. You rank your data, you find the midpoint, the 50th percentile, and that is the median household income, which is very different from the mean household income. These are quite different because these are not a normally distributed quantity. Not only that, the median gives you actual information, and the mean often does not. You saw how my students were actively misinformed by assuming the mean value is typical. For example, suppose you're a patient and you're told the average survival time with your type of cancer is 2 years. What can you assume? What's the take home for you? And the answer is, again, nothing. It's just like the tax return thing. What if 9 patients die within a month, but the 10th patient lives 20 years? Then the average survival time is 2 years. But that's not helpful to you. But if I tell you the median survival time is 2 years, now you have something you can use. You know that you have a 50-50 chance of making it to 2 years. That's a useful piece of information for your life planning. Why don't we use the median more? Because math professors can't prove theorems about the median. Because it's an if-then statement. It's not a form. There's no formula for the median. There's a procedure for calculating the median. But math professors can't prove theorems about the median. Therefore, you can't use the median because we can't prove theorems about it. Now, that's what we call backwards, I think. They're telling you what scientific measures you can and can't use based upon what they can prove theorems about. So I said the late 20th century was the big watershed, and this was the great paper that changed everything. Uh, Brad Efron is the chairman of statistics at Stanford. And look at the title of their article, Statistical Data Analysis in the Computer Age. So you ask, what were we doing before? And the answer is, most of our familiar statistical methods were designed to be implemented on mechanical calculators. Modern electronic computation has encouraged a host of new statistical methods that require fewer distributional assumptions, no more normal distribution assumption, and can be applied to more complicated statistical estimators. We welcome the mean and not just we welcome the median and not just the mean. What's the trick? Traditional methods of mathematical analysis are replaced by specially constructed computer algorithms. Basically, if you want to find out how often something happens, create the world, simulate the world, and see how often it happens. Excellent textbook by Friedman, Pisani, and Purves makes the same point. In Pearson's time, 1920s, there were no computers to find the chances, so he developed a method for approximating the p-value by hand without having to do a computation that was, by the standard of his time, quite formidable. But by the standard of our time, you can do this on your phone. So why are we doing this? Why are we clinging to pre-computer methods to prove theorems which completely cripple our ability to describe the data? So let me just close by showing you what this would look like. So I have two groups, and I have a control group and a treatment group, and I'm looking at what the drug B did to the T cell counts in a Petri dish. And here is my data. So the first thing I do, which I can't do if I'm doing a t-test, is I have to look at the data and I have to say, what is the distribution? Oh, look, this is kind of skewed right. This is kind of skewed left. I can't use a t-test. Just t-tests fail. So what can I do? Number one, I'm not committed to the means and the standard deviations and all of that. I have my group A and my group B. I plot their distributions. I look at them and I choose a group measure. Maybe this is the mean. Maybe this is the median. I then calculate my effect size, the observed result, which could be MA divided by MB divided by MA, could be MB minus MA. And I now have an effect size, delta obs. Next question is this difference, delta obs, large? After all, any two groups are going to differ on something by some degree. So the question is large relative to what? And the answer is large relative to what you might expect from pure randomness. So the question is, how big a difference would you expect to see if A and B were just two random samples from the same set? Now that's if A and B were normally distributed and you used a mean and this and that and this, then that question is answered by the T formula, which is unintelligible gobbledygook. And the student cannot possibly understand the gamma function, which is the infinite integral of beta. The message of the teacher is shut up to the student, is shut up and calculate. And I'm not comfortable with that. I don't think that's good teaching. I don't think that's a good understanding. So how do we answer the question? How big a difference would you expect? We take group A and group B, and we combine them into a big box, forgetting where they came from. So now we just have a big pile of data. Then we do what's called resampling. or sometimes bootstrap. We take this big box of A and B combined, and we sample a pseudo A and a pseudo B at random with replacement out of the big box. This is two random samplings from this distribution. Let's calculate the effect size there. Let's call that delta sub 1. Okay, that's one estimate. Let's repeat that 10,000 times. This is going to take 2 minutes on a laptop, except if it's a fast laptop, in which case it takes about 30 seconds. So now we have 10,000 estimates of how big a difference would arise between these two groups using these measures if there were no difference, if we're just randomly sampling from the same universe. So we take our delta obs, your observed result, and we ask, where does it rank in the 10,000 simulated deltas? And if your actual delta is bigger than 95% of the simulated deltas, then your actual delta is significant at p less than 0.05, because it or results bigger than it occurred less than 5% of the time. And that's what p less than 0.05 means. So we make this histogram of the delta i's. Here is our delta obs, the actually observed result. In our randomized 10,000 randomized simulations, a difference this big never occurred. And so now we can say, result, the median T cell, we're using the medians here. The median T cell count was improved under the drug by approximately 10 cells per unit area, and P is less than 0.0001 because this never occurred once in 10,000 simulations. This is an understanding of statistics. If you want to see how often something occurs, set up your assumptions and simulate tens of thousands of times and see how often it occurred. So once again, we're in the same kind of situation. We have 19th century statistics with all of these crippling assumptions, and we have late 20th century statistics, which frees us, freedom of measure, I like to say, measures other than the mean and standard deviation. All distributions are welcome. Skewed distributions, bimodal distributions, and we can accept them easily because we're going to randomize the world to create the test against which we're going to compare the actual data. We don't have to make crippling assumptions to derive gobbledygook formulas. The student comes to you and he says, "Oh, I'm teaching the t-test." So you say, okay, calculate t. It's the difference of the means divided by the standard deviation and multiplied by the square root of n. And then plug this t into this formula for using the gamma function. And the student is saying, what is all this? What is this? And you have to just throw up your hands and say, sorry, I can't, I really can't explain this. So it's bad science. I've argued two things. It's bad science and it's bad teaching. And so the question is, why are we doing it? Thank you very much.
Thank you so much, Alan. I hope you enjoyed this. This is like the third time I have heard Alan speak about these topics, and each time I'm equally enthralled and I learn so much. So thank you for joining us.